And so we're very glad to have Tashi Walde here today, who will be talking about higher Segal spaces via higher excision. So you can start when you're ready, Tashi.
Okay, yeah, thank you very much. Thank you for inviting me to speak here, John. So I'm happy to be here. And so today I'm going to talk about things I did in my PhD thesis regarding higher Segal spaces, which are these higher homotopical structures. But before I can get to them, I have to give a little bit of background, starting with the classical Segal spaces, which probably many of you know, but just to make sure I'll quickly recall what we're talking about, since maybe not everybody has seen this. So to fix some notation, so we have delta, that's the simplex category, which for me will be the category of finite, non-empty, linearly ordered sets, which I view as a full subcategory of the category of categories. And up to isomorphism, every object is of this form, which is just a set with the elements 0 up to n with their obvious order. And the main point for this talk is that functors out of the simplex category to set or later to some other targets can encode algebraic structures in very efficient ways. And the first main example of this is the nerve construction, which takes a category and assigns to it a simplicial set, so a functor from delta up to set, by mapping a category to this hom functor, where in the first variable we plug in our coset viewed as a category. And the main point about this is that this functor is fully faithful, so the category is completely encoded in this nerve, and the essential image can be characterized as what are called the Segal simplicial sets. And so this is the notion we're going to be generalizing. And so an object is called Segal if it satisfies the following condition. So the n cells of the simplicial object, so the value at n, is isomorphic via these canonical maps, where inside this set here, I have these sets of the form I minus 1i, and these induce a map from here into this fiber product. And this should be a bijection. So let me tell you how one should think about this. So I'll continue on the left side. So one can recover a category C from its simplicial set as follows. So the object of C are just the value at 0, and the arrows are the value at the set 0, 1. And then the two maps, which the two inclusion here induce the source map and the target map of the category. And the composition, it's given as follows. So if I have two composable arrows, so I have an arrow which is an element in x0, 1, an arrow which is an element in x1, 2. So these two objects are isomorphic. And if they're compatible, so the source and the target match, then by the Segal condition, I can pull it back along this bijection and get a 2 cell, and then I can evaluate at the long arrow down here. So schematically, you can think you have these two composable arrows, you fill it to a triangle, and then you evaluate at the lower arrow. And this gives you the composition. And the associativity is encoded in this maybe slightly intimidating diagram here, where if you start with 3 arrows, then you can do various things. You can first fill, for instance, this left triangle, or you can first fill this right triangle, and then you can keep filling. You can fill this triangle here, or you can fill this triangle here. But since all of this commutes and we're inverting these maps, then overall this composite will be one side of the associativity and this composite will be the other. So I lift this up. You can look at this. Exactly. So this is the classical notion of Segal simplicial sets, which encode categories. And now in homotopy theory, we now replace the target, the category of sets, we replace it by something which carries homotopical content. So I personally are mostly working with infinity categories, but one can do the same thing with a model category or some other notion which allows one to do homotopy theory. And so, for instance, this C, which is our target, can be something like groupoids or the infinity category of spaces, spectra, or even the infinity category of infinity categories. Yeah. So if you're not comfortable with infinity categories, you can also think that C is just an ordinary category. Much of the talk will still make sense in this way. Okay, and so the the thing for us here is that if we have a simplicial object, so that means a functor from the simplex category in C, then in fact we can evaluate this not just on delta op itself, but on all simplicial sets. And this is given by a homotopican extension, which is just a fancy language for the following formula down here. So every simplicial set can be, let's say, K, can be written as a co-limit of simplices, and then you can evaluate X at those simplices and then take a limit and glue them back together. So maybe it's easiest to just keep in mind this following small example where X at this square, X at a commutative square, I can write the commutative square as gluing together two triangles, and X I can evaluate it a triangle, which is just a set 0, 1, 2, and then I can take a fiber product or homotopy fiber product over this edge along which I'm gluing. And so now we can reformulate the Segal condition as follows by saying that the canonical map from, so if I have the n simplex, inside the n simplex, I have the spine consisting of all the vertices and these maps connecting them. This is a simplicial set. I can evaluate X on this, and this canonical map induced by the inclusion needs to be an equivalence. So let me scroll up here so you can still have this up. Okay, and now the main point about the Segal object is that they encode coherent associativity. So now this associativity square diagram here, since we're now taking values in some category with homotopical content, these bijections will now be weak equivalences, and all these squares will no longer commute on the nose, but only up to some specified homotopies and so on. But this will encode then some higher coherence. And for instance, one famous result is that Segal spaces, so Segal objects in the category of spaces plus the technical completeness condition, these really encode infinity categories. And now let me give you also another example, which will be instructive later, which is actually kind of Segal's original example in a sense. So if we have, for instance, A being the category of projective modules over a ring, then we can get a Segal object as follows, where to this n, we associate the following groupoid, the groupoid which consists of n many objects in my category A, and then choices of direct sums. So A1 plus A2, A1 plus A2 plus A3, and so on. So this diagram continues. I fill it with all possible choices of such sums. And then this gives me a functor from the simplex category to groupoids, where this is a groupoid with the obvious maps between two different such diagrams, the obvious isomorphism between two such diagrams. And in fact, we can even extend this to Segal's category gamma by permuting these AIs, but that's maybe not so important now. So this example you should keep in mind for the next slide. Okay, so the upshot here is that these classical Segal objects, they're used to encode associative structures. For instance, this Segal object here, it encodes the associative direct sum operation on projective modules. And so now I'm gonna start with two Segal objects, which were introduced by Dykhoff and Kapranov, and also independently by these three authors, Galvez Carrillo, Koch, and Tonks, under a slightly different name. And the idea here is that sometimes one has operations which are defined not, so if I take two inputs, I don't have a unique output, but I have a multi-valued output. And the main example to contrast with the direct sum is extension of modules. So if I'm given two modules, so let's say A and B are two modules in the category of modules, or in some general Abelian or exact or whatever category, then I can say, okay, the product of A times B is every possible E which fits into a short exact sequence A, E, B. And of course, now there are many such modules. This multiplication is no longer unique, but in some sense, it's still associative. That's the main point. And so what do I mean by saying this is associative? So if I look so if I start with A, B, C, so I have A, B, C, and now I look at two possible things I can do. I can do first an extension of A by B, and then an extension of that resulting E by C. So that will give me stuff of this shape. Or I can start with A, B, C, take first an extension of B by C, and then an extension of the resulting module with A. And the point is that there's actually a canonical bijection between these two pieces of data, and one can interpolate between both of them by looking at data which looks like this. So I have this full extension. I have A extended by B, B extended by G, and then such a square here, which is both a push out and a pullback. And by the third isomorphism theorem, in fact, the canonical forgetful maps here and here are actually bijections. And you can recover, for instance, this missing G here. I can, for instance, recover as the push out of this span here. So like you see here, the formula, I can recover this missing G as the push out of F and B over E, or vice versa. Here, I can recover the missing E as this pullback. So the point being here that if I scroll down, and I'll put the other one up here so you can still see it. If you scroll down, the point being that this data I can think of as one side of the associativity equation, this one as the other one, and there's a bijection between them, or or an equivalence of groupoids depending on the context. And one can sort of capture all this data together in the so-called Waldhausen S construction, which is a simplicial object, and the target depends a little bit exactly what one is doing. Sometimes it goes to groupoids, to spaces, sometimes even stacks. This depends a little bit, but this is not so important. The point is that we send n to such big diagrams, which, if you see, it's exactly this sort of master shape, which encodes not just one side of the associativity, but somehow an unbiased version where I have all my objects plus choices of extensions of each pair of them, and then extension of the extensions and so on, all the way until I have this big shape. So this is the Waldhausen S construction, and the point about this construction is that it satisfies what is called the two-Segal condition. So I will formulate the precise condition later more systematically, but let me just first give you the main example of this, one of the instance of this two-Segal condition. It tells you that, so if you have X and you evaluate it at such a square, then you will get this side. So you see here you have A and B together with a composite of with a product of E being A times B, and then an F, which is the product of E and C. So you see that's exactly this left side. Or you can do it the other way around. You can have A, B, C, and then you can have G, which is B times C, and you can have F, which is A times G. Or you can have sort of the unbiased version where you have A, B, C, and all their possible composites. And the main point is that these two maps, which are these two maps, are equivalences. And if you're familiar with geometry, then maybe you will also recognize that the interplay, the move from here to here is exactly the 2-2-Pachner move, where we have a square with a triangulation in one way, and we can flip the triangulation to the other way. And in fact, this is also no coincidence, and these sort of Pachner moves appear here later. Okay, so this is the first instance of such a two-Segal condition. I will write the full conditions out later, but let me first tell you why these two-Segal objects are somehow interesting. Let me scroll here on both sides so you can still see. So the main, one of the reasons to work with two-Segal objects is that one can take convolution algebras for two-Segal objects. So the idea here is, so assume we have a two-Segal object in our category C. So it's a simplicial object which satisfies these two-Segal conditions, and in particular this Pachner interplay, so which is some sort of associativity. Then we can turn this two-Segal object into a module by a linearization procedure. So imagine you have some sort of cohomology theory which starts in your category C and goes to some linear setting like vector spaces, R modules. Of course, the exact context depends on what exactly you're doing. Then you can define this sort of convolution product where if you think of, you have a cohomology class and another cohomology class, and you want to take their product, then you say, okay, evaluating at E, you just write down this usual convolution formula where you take all possible products of A times B equal E, just that now this is a multi-valued product. So there's now not just a single, so so this space refers to all possible A's and B's such that their product is E. And of course, since it's a multi-valued product, it's slightly more general than the usual convolution formula, but the associativity statement here will still make sure that this product is associative on this vector space R module or whatever you're doing here. And these are called Hall algebras when you apply it specifically to X being the Walthausen S construction. And these are important algebra and representation theory. But I don't really have time to go that much more into this. Okay, so these two Segal spaces can also be compared to other nice algebraic or higher algebraic structures. So one of them, this also was part of my PhD thesis. So two Segal spaces, so where we here specifically take values in spaces, they can be faithfully embedded into colored non-symmetric infinity operats. And one can also characterize the essential image as certain operats, infinity operats, which satisfy certain invertibility condition. I don't have time to go into this, but the main point being here is that this multi-valuedness of the two Segal spaces, one can really also encode it in the language of operats. And another related theorem by Walker Stern, who is also my mathematical sibling, so to speak, also Dyckerhoff's student, he proved that two Segal objects in general can be characterized as algebras in the category of spans in C. So yeah, this is not so important now, just to sort of show that one can also encode these two Segal objects in different way. And in some sense, these two Segal objects are relatively well understood. So the thing you should really remember from all this is that two Segal objects are a way to encode multi-valued multi-valued structures which are associative up to coherent homotopies. That's the upshot of this discussion. Okay, so now that I've somehow talked about one and two Segal spaces, let me now talk about higher Segal spaces, which are somehow the natural continuation of this hierarchy. So a priori, it might not be completely obvious how this hierarchy looks like, but there's actually a very nice description, which is how Dyckerhoff and Kapranov originally introduced these higher Segal spaces, and then it was kind of worked out by Pogundke, that these higher Segal spaces, they can be introduced very nicely by the combinatorics of so-called cyclic polytopes. And so let me scroll here just a little bit so you can see both pictures. So a cyclic polytope is defined as follows. So there's this map which sends a t to this tuple with t squared and so on. There's a map from R to the D. And then you take d many points on this curve and then take their convex hull. And this gives you a convex polytope in R to the D. So for instance, here on the left, I have a two-dimensional picture. Here I have a three-dimensional picture where the curve kind of looks the same because I can't really draw it, but you should imagine this curve being in 3 dimensions. And if you have 4 points on this, for instance, the convex hull will be just a 3-simplex. And so let me keep these pictures up. And the main thing about the cyclic polytopes, which we are going to need for today, is that if you look at the boundary of this polytope, so this outside, then you have an upper boundary, which is the part you see if you look from above, and the lower boundary, which is the part you see if you look from below. So for instance, if you look at this picture on the right here, if I look from below, then I see this picture. I see somehow a line with these subdivisions. And if I look from above, I just see this interval like this. Or similarly here, let me scroll just a little bit so you can see this. If you take the simplex, if you look from below, then you see a square, or I guess a slightly distorted square, but it's still somehow, it's a foregone, together with a triangulation, which comes from looking from below. And if you look from above, you see the same outline, but now with this different triangulation. Somehow these are the two faces of the two ways of looking at the 3 simplex. And so let me keep this up. So as I said, the main point is that the boundary, it is subdivided into this lower part and this upper part. Of course, one can write down explicitly what this means, but I hope this picture is intuitive enough. So we have this upper boundary and this lower boundary, and these are simplicial complexes. And so now using these boundaries, one can define these higher Segal spaces. So note that these boundaries, they come equipped with a triangulation with just as simplicial complexes. Okay, and so here's the definition. So a simplicial object X in some infinity category C or in some category C is called lower D Segal if X sends the canonical inclusion from the lower boundary into the n simplex to an equivalence, or then upper D Segal, it's the same but with the upper boundary. So I'll give an example in a second. Maybe this is more instructive than the actual definition. So let me scroll down to the example on the left. So for instance, being one Segal, if you see here, sorry, I shouldn't have scrolled here. So here, this is the second cyclic polytope, and one of its boundaries, the lower boundary, it looks exactly like this. So it's an interval subdivided into these pieces, and being one Segal means exactly that the value on this subdivided interval is equivalent to the value on the n simplex. So this really recovers the Segal condition from earlier. Or if you look at these two triangulations, which come from this three-dimensional polytope, then you see exactly the two Segal condition from before. So on the left side, we have this triangulation like this, and on the right side, we have this triangulation like this. So we really have this Pachner move, both of the sides of this Pachner move. And more generally, what you get is that you can get all possible triangulations. Okay, this is, yeah, more generally, you can show that you can get all possible certain triangulation of the n-gon, and then you can prove that from this it follows that you also have all possible triangulations. Okay, and here there's a picture of the two triangulations of the three for the three Segal conditions. Here's already a little bit harder to see. So this is a three-dimensional polytope, which you can write either as the union of two three simplices or of three simplices. And this is then the 2-3 Pachner move, comparing the left and the right. Okay, so, but maybe, yeah, this is maybe, let's just keep this example up so you can look at this. Okay, and the main, so there's a nice class of example which was worked out by Pogundke, which is somehow a higher dimensional version of this Waldhausen S construction. So this, I don't have time to really explain this, but you can somehow write something similar, and you have a higher Waldhausen construction assigned to some, abelian or exact or something category A, and this has the property that its geometric realization gives you a k-fold delooping of the K theory of A, for those people who know about this. So one of the reasons to study that's why the Waldhausen S construction was introduced in the first place, was to define K theory. Okay, and so before I move on, so let me just, there's a very nice combinatorial criterion for sort of detecting how these boundaries look like. And I'll write it down now, and maybe I'll remind you later. So it's actually very simple. So if I want to know which, if I'm in the odd case, so where I'm in the odd dimension, and I want to know how does this upper boundary look, the lower boundary look like, then it essentially consists of all possible disjoint unions where I have k many pairs of consecutive elements. So this is maybe a little bit hard to parse. So let me just show you an example here. So for instance, if you have 4, which consists of the elements 0, 1, 2, 3, 4, then the simplices you're looking at are, you look at all possible pairs of consecutive elements, and so you get these 3. So you have 0, 1 and 2, 3, 0, 1 and 3, 4, 1, 2 and 3, 4, and these will be the simplices. Or even simpler, in the one-dimensional case, you just have 0, 1, 1, 2, 2, 3, and 3, 4, and that's exactly the one coming from the one Segal condition from the beginning. Okay, so there's this nice hierarchy. Sorry, let me scroll up. Sorry, I should have So, okay. So today I want to focus on two parts of this hierarchy. So we have the lower 2k minus 1 condition, where the first stage of, so the lower one Segal condition was really just the classical Segal condition. And then on the even side, we have the 2 Segal condition, and these two I kind of a little bit sketched. They're relatively well understood. So this one is very well understood. This one is also quite well understood in terms of operats, for instance, or algebras of spans, or similar things. And now I want to sort of try to explain how this hierarchy, these two hierarchies as a whole, they can be both understood in terms of excision, so in terms of some sort of manifold calculus, which I will explain what this means and where this comes from. Okay, but so yeah, so the upshot is that there's this hierarchy which is defined in terms of this nice combinatorics of cyclic polytopes, but it's still a little bit unclear what this really means and why this really might be interesting. And I'm going to try to convince that actually this has a very intrinsic meaning in terms of category theory of the simplex category. So if you care about the simplex category and you care about basic categorical notions such as pullbacks, pushouts, and so on, then hopefully this will end up in a characterization which will be reasonable and somehow interesting. Okay, but before I can do this, I have to do an interlude, because I would imagine that not everybody is familiar with manifold calculus. So I have to first explain a little bit what the main idea is of manifold calculus. And then the idea is that we want to do some sort of analogy of manifold calculus, but for the simplex category. Okay, so here's the setting. So with a note by man, let that be the topological category of smooth manifolds and embeddings. And we can also think of this as an infinity category, or but for instance, I will think of this as an infinity category, but this is not so important. Okay, so and now we're looking at pre-sheaves on this manifold calculus, so contravariant functors from the manifold calculus to our chosen target. And such a functor is called excisive if the following holds. So whenever we have an open cover of a manifold by two opens, then if I apply x to this square given by m, the two opens and their intersection, then this square has to be a homotopy pullback, or I'm not going to keep saying homotopy, it's going to be a pullback in C. So in other words, what this means is that we can compute the value at M by computing the value on U1, on U0, and on their intersection, and then gluing back together by a fiber product. So for instance, you know, I have this little picture here. To compute the value on a torus, I just have to compute the value on these two cylinders and then glue along their intersection. And of course, this is a very natural condition which gives rise to homology theories and similar things. So basically, it's some sort of condition which tells you that you can decompose your manifold and then just compute your functor in very easy pieces. So for instance, if the target is some derived category, then after taking homology, this will yield the usual Mario-Vittori's sequences, long exact sequences. Okay, and in this setting, the main example is, for instance, if you look at if you fix a manifold and you look at the functors of immersions into your fixed manifold, then this is excisive, because to give an immersion from here into something, such that they agree on the intersection is the same as giving an immersion of the whole manifold. However, if we, instead of looking at immersions, we look at embeddings, then this is no longer excisive, because if you have an embedding on this, an embedding of this, such that it agrees on intersection, you will still be able to glue them to a map from here, but it might no longer be injective. It might no longer be an embedding of the whole manifold. And the point is that being an embedding is a global condition. You cannot just check this locally. But the main idea why why this manifold calculus came up is that one should be able to approximate some arbitrary sheaf, such that the one of embeddings, by a hierarchy which starts with these immersions and then has something in between. And so the idea is we have arbitrary functors, and then inside here we have excisive ones, and then there's a notion called polynomial of degree of a certain degree, which I will explain in a second. And the idea is that then one has these polynomial approximations. And for instance, if I take the excisive approximations of embeddings, then that will yield you exactly immersions. And so the idea here being that if we start with some arbitrary x here, we will get by these approximations, we will get a tower starting with a constant functor, then an excisive functor, and then more and more complicated functors, which hopefully in the end give us some information about our original functor x. So I still need to tell you the definition. Sorry, let me scroll like this. I still need to tell you the definition of a polynomial functor of degree smaller equal k. So I already told you what it means for a functor to be excisive. To be polynomial is a similar condition. So now look at, so if I have a manifold M and I have an open cover by k many pieces, but I don't just want that that in total they cover my manifold, but every pair of them needs already to cover my manifold. So equivalently, this is saying that their complements are closed and pairwise disjoint sets. Then in this case, I call a functor polynomial of degree small equal k if the value at my manifold can always be written as the limit of x over all. Again, it's now just a more complicated limit where now I go over all possible intersections of these u's I started with. So here I have a picture on the left, which somehow explains a little bit this interplay, which goes on in manifold calculus. That so here I have three closed sets which are pairwise disjoint, and then their complements will be these u's. And so what I can do is I have my manifold, and I can cover it by a small number of pieces, in this case exactly 3 pieces, but these pieces themselves might still be kind of complicated, and their intersections might still be kind of complicated. But then to evaluate on M, I can just evaluate on these pieces and put it back together. However, one can also somehow go to another extreme by saying I cover my manifold M by a very big number of opens, but all these opens are now supposed to be very small, and they're supposed to be disks, and their intersections are also supposed to be disks. And this is what is called a good K cover, which I will define in a second. So, but somehow we see we have these two extremes. On one side, we have a small number of things covering my manifold, but they're potentially complicated. And on this other side, we have a very large number, but they are very simple. And this interplay we want to mimic in the simplex category. So before doing this, let me give you this definition of such a good K cover. So a good K cover of a manifold is a cover M by opens. So now this is no longer necessarily a finite union, such that all of these are open, and such that not only does it cover M, but actually every subset S which has cardinality at most K has to be contained in one of these UIs. So equivalently, you can say that it's still a cover of the Cartesian product. So if you just take the k-fold powers of each of these opens, then this should be a cover of the Cartesian power of M. And such a cover is called good if all finite intersections of such opens are diffeomorphic to a disjoint union of at most k disks. So if you look at this picture, maybe it's a little bit hard to see, but see there are these color coding. So for instance, one open could be these 2 disks, another open could be these 2 disks, and also their intersection need to be disks. And here's a theorem of Boavida and Weiss, which show that somehow requiring gluing with respect to these sort of things is the same as gluing with respect to these sort of things. So the theorem is that a polynomial functor of degree small equal k, that's the same thing as saying that I can glue for each good k cover. So whenever I have a good k cover, then the value of my manifold can be reconstructed as the limit of the value of all the finite intersections, which now note these are now all disjoint union of disks. So the value here is hopefully very simple, but now of course I'm taking a limit over a much more complicated diagram. So the trade-off is that here I take a simple limit, but potentially over complicated things, and here I take a very complicated limit, but over simple things. Okay, let me skip this this lemma here. So now I want to move to the how do we translate this to manifold to the simplex category? And for this, I'm also going to put up a picture because maybe that will be more helpful to understand. Otherwise, these things I've written here might be a little bit mysterious. So the idea here, and this is more like an informal idea. It's not so there's. I mean, maybe one can make this connection precise, but for now, let's just keep it informal. But the upshot is this will lead to true theorems about the simplex category. So I want to think of each element of the simplex category as a sort of manifold in the following sense. So I have my object of the simplex category. So it has, and I want to think of it as a manifold like this. So the points of my manifold are gonna be pairs of adjacent elements. So for instance, this green point on the left, this green point here, it's the element, it's the point 0, 1. And then I have the 1, 2, which is this point here, and so on. Then I declare an open set in my manifold to just be a subset of my n. So for instance, this is so here I have the open set 1, 2, 3, 1, 2, 3. And this contains, which points does it contain? Well, it contains those points which are completely contained in this open set. So for instance, this open set would contain the points 1, 2, and 2, 3. So that's what this line here says, that a point is contained in my open if and only if this corresponding subset is a subset of the open. But note that there might be open subsets which contain no points. So for instance, the open just 4, it would look like this, and it would contain no actual points of my manifold. And now we say that that two open subset cover my manifold if every point lies either in one or the other. But note that this is stronger than saying that their union as subsets is equal to n. Okay, so this is now, this is not a real manifold in any sense, but somehow we can, if we take this analogy seriously, we can actually learn something about the simplex category. Okay, so the first definition is that now we can mirror the definition from manifold calculus, and we can say, okay, if we have a collection of subsets, then I want to say that each pair of them is an open cover of my manifold. That's what this condition here says. And so if one spells this out, what this means, it just means that for each I, there's at most one of these which does not contain this point I1, I. And then it would mean that if I take any two of them, that point will be contained in one of them. So, and that gives us now the definition, we can now formulate this theorem, which connects back to the two Segal objects. So we can now say what it means for a functor, for a simplicial object to be polynomial of degree smaller equal k. Well, we know now, so we can just copy the definition of manifold calculus. So a functor is polynomial of degree smaller equal k if and only if the value at n is equal to the value of all these, it can be computed as a limit of values of all these intersections for each collection of subsets of n, which is compatible. Where compatible, I remind you, is just a condition saying that every pair of them covers my manifold. So it's really if I scroll up, it's really the condition, it's really the condition, this condition here. So the one where I have my manifold and I cover it by a collection of opens such that every pair of them still covers my manifold. And on the other side, we have this Segal condition. And in fact, this Segal condition, if one works this out, it really corresponds to the second part of the picture. So let me just try to illustrate this. So if I am given k many points, so let's say in my manifold, so there are going to be pairs of adjacent elements. So so I have one pair, another pair, I have k many pairs. Then I can take an open set which contains the minimal possible. So I can just take I can just take an open which just contains these points, and this will be the analog of such a good cover of my manifold. So if you have a manifold and you have some collection of points, then what you really like to do is you want to take as small as possible open set around each of them. And that's what we're doing here by taking a minimal open around each of these points. And then we will get an open set, which is of this form. So it will be a collection of pairs of adjacent elements. And if you now remember back, I told you that these opens of this form, or these subsets of this form, are exactly the ones which appear in the theory of which appear in the triangle. In the simplicial complex from this cyclic polytopes. So somehow we have this same interplay here and here. It gives us an interplay between these Segal objects and these functor, which I call polynomial. And this is the first theorem. However, this is not very satisfying yet, because I promised you that I was going to give you some intrinsic categorical notion just to do with the simplex category. And that's what I'm going to explain next, that actually this polynomiality condition, it has a very nice categorical interpretation in terms of the category theory of the simplex category. So let me scroll down here. So let me maybe skip this.
Tashi?
Yes.
Before you continue, can you recall maybe, you probably said that earlier, but
yeah, sure, please.
Why we focus now on the lower rather than the upper odd ones, and why the lower upper thing did not appear in the even case?
So this is a good question. There are two reasons. First of all, the main examples of higher Segal spaces which appear in practice are either even, both-sided even, or lower odd. So that's one reason on focusing on these two hierarchies. And the second, more conceptual reason is that all the higher Segal conditions can actually be reduced by a very simple procedure to the lower odd ones. So you can, if you know the lower odd ones, then in a very precise sense, you also know the even ones of one dimension higher, and also the upper odd ones of 2 dimensions higher.
So by no, you mean if an object satisfies the lower 2k minus 1, it also satisfies?
Not that exact object, but a slightly so the exact statement is something like an object is 2k Segal if both its left and its right path space are lower 2k minus 1 Segal. It's not so important what exactly it is. The point is just you can always reduce to the lower odd one for a slightly modified object maybe, but but you can always reduce to this. So in some sense, the lower odd one is the most fundamental of all, and the other ones you can always reduce to that one by a very simple procedure of taking a left or a right path space. Okay, thank you for asking. Maybe I should have clarified this.
2k Segal means both upper and lower.
Exactly. And these are the ones which appear in practice. So as I said, this higher Waldhausen construction, it is both upper and lower 2k Segal.
Yeah. All right.
And I will say something about the even case in a second. That's where the cyclic category comes in. I won't have time to do this in detail, but I will mention this. So I now promised an intrinsic characterization of what are these limits which appear here, and in fact they just come from push out and pullback squares in delta. So it's a relatively easy lemma to see that if you have such a square, so you have an object in delta together with 2 subsets and their intersection, then this square is this square is a push-out square if and only if these subsets are compatible in the sense I said before. So if they correspond to like a cover. And note that this is always a pullback square, kind of by definition, because I took this intersection, and in the simplex category, this is always going to be a pullback. However, there are also other push-out squares which are not just which don't just come from subsets and their intersection. So for instance, this square here is a pullback square, is a push-out square. So these 2 squares are both push-out squares, but only one of them is a pullback square. So maybe it's not so important now why, like maybe I won't focus on this, why exactly this particular square. But the upshot is the following: that what one can prove is that by just explicitly characterizing the push-out and pullback squares in delta, is that a simplicial object is Segal, so really like the classical Segal one, if and only if it sends all bicartesian squares, so bicartesian means it's both pullback and push-out, to pullback squares in the target. So this condition, you see, it's a purely categorical condition. You're just saying certain limit/co-limit diagrams are sent to limit diagrams. And this actually turns out to be equivalent to the original Segal condition, which was defined in somehow this, very specific way. You had some very specific diagrams you just write down, but maybe it's not completely clear why those. And now the upshot is that actually an analogous theorem holds for all higher Segal conditions as well. And this is exactly the theorem I want to present. So to do this more generally, if I have a cube in the simplex category, so a cube I think of as a map from the power set poset of some set S. So this is the power set of S with its inclusion relation. So this is a cube. And if I have a poset as a functor into delta, then this is a cube. And such a cube is called strongly bicartesian if every two-dimensional face, which can be written like this, but you should really just think a two-dimensional face, is bicartesian. So it's both a push-out and a pullback. Or equivalently, you can say you have this big cube, which now I've only drew a part of. So I have like this initial part and this terminal part. And of course, there's all this stuff in the middle. This cube, so this strongly bicartesian is equivalent to saying that the value on this whole cube is a right Kahn extension of its restriction to this terminal part, so where I only have the last vertex plus the ones directly before, or a left Kahn extension and a left Kahn extension of this initial part, where I only have this initial vertex plus these. And then everything in between has to come by Kahn extension. So for instance, the value here has to be a push out of this, and so on. So you start on the left and keep taking push-outs, push-outs, push-out, and everything else needs to come from taking two-dimensional push-outs, but also it has to come from taking two-dimensional pullbacks. So that means every square is both a push-out and a pullback squares. And if we have a square which is of this specific shape where I have some subsets of n and then take all their intersections, one has to pass to some op here, but that's just, so a power set is canonical isomorphic to its opposite, but that's just so that this functor works out. So this cube, which contains all the intersections, it is strongly bicartesian if and only if this collection is compatible. So this compatibility condition really amounts to saying that this canonical cube, which you get, it is strongly bicartesian. So every two-dimensional face is both a push-out and a pullback. And so this leads to this theorem, which now contains the actual categorical condition. So a lower 2k, so a simplicial object, the following are equivalent. It is lower 2k minus 1 Segal. It is polynomial of degree smaller equal k. So that means it sends these compatible intersection cubes to limits. And third, now comes the sort of very categorical condition. It sends all strongly bicartesian cubes of dimension k plus 1 to limit cubes. So now you say, okay, you have all cubes where each face is a pullback and a push out, and this needs to be sent to a limit. So this is a condition which purely refers to the categorical structure of delta. And for those who know about Goodwillie calculus, you can compare this to the notion of, in Goodwillie calculus, you would not require bicartesian here, but only co-Cartesian. But but this is kind of similar to this, which is why this condition, for instance, I would call it weakly excisive. But this is not so important, so you can just think about this condition as written. Okay, so and you see this characterization, it mimics the manifold calculus, where somehow this upper thing corresponds to the good covers, and this lower thing corresponds to this chopping up into k many pieces by taking out disjoint closed subsets. Okay, so so this somehow explains the odd ones in terms of this condition here of bicartesian cubes. And let me now quickly mention the even ones, because they also have a very nice description. Of course, one can reduce them to the odd ones, but one can also show that they come from the category theory of another category, which is very closely related to the simplex category, namely the cyclic category. So let me just quickly tell you what the cyclic category is, at least informally. So the cyclic category called lambda, it is the category of now not linearly ordered sets, but cyclically ordered sets. So the elements are these things called n, which they are ordered in this cyclic way. So I don't really want to say what this means precisely, but hopefully you have a picture. You have a successor operation, which at some point comes back, and this gives you a cycle. And the morphisms, one way of sort of writing these explicitly is to say you have maps from the circle to the circle, which preserve maps, which preserve a certain number of marked points on the circle. And these maps have to be monotone and of degree 1. So they have to wrap around exactly once, and they're not allowed to like come back. They have to really go continuously forward. And they have to map these marked points to the marked points. And then you take this up to homotopy. But really, you should just think of these cyclically ordered sets. And then, there's a good notion of maps between them. So the two main points to keep in mind is, so the automorphism group of this object is exactly the cyclic group of order n+1, and the automorphism are just given by rotating the cyclically ordered set. And the second thing to keep in mind is that giving a map to 0, so if you have such a cyclically ordered set, and you go up, if you have to 0, so 0 is just a single point with its trivial cyclic order, then all of these points will be mapped to 0, and almost all of these arrow will be collapsed, but there will be one arrow which is left over. And specifying this one place where you do not collapse, basically you can think of, you have the cyclic order and you cut it open at this place, and so what you're left is a linear order. And so this shows, of course, you can make this precise, and this shows that the slice of lambda over 0 is exactly the simplex category. And so in particular, you get a map from the simplex category into lambda. And so the way you should think about this is that a cyclic object you can think of it as a simplicial object with additional cyclic symmetry. So here I've drawn a simplicial object, how one would usually draw it with its faces and degeneracy maps. And then additionally, each object has a cyclic automorphism group, which is this one. So here I have an action of the cyclic group of order 2, here of order 3, and so on. And in terms of simplices, you should think of this as, for instance, here you have the two simplices, and you should think of this action as rotating these simplices in a cyclic fashion. And this is all made somehow, the compatibilities are somehow encoded in the combinatorics of this cyclic category, lambda. And so the theorem the analogous theorem as before is that the even two Segal conditions, which are often the ones one is actually interested in, because for instance, in the examples, that's the one which come up, they are exactly those functors which are weakly excisive with respect to the cyclic category. So what I mean by this is that you have to take those cubes in delta, which not only are they strongly bicartesian, but they remain strongly bicartesian once you pass to lambda. So you have to pass to lambda, check if your cube is strongly bicartesian there, and if so, then your functor is required to send it to a limit. So a functor is weakly excisive if it sends to limit diagrams in C those k+1 cubes which are strongly bicartesian in lambda. And so as a corollary, if you start with a cyclic object to begin with, then it is 2k Segal, by which we mean its restriction to delta is 2k Segal, if and only if it is really weakly excisive. So it sends strongly bicartesian cubes to limit cubes. So this again is a very simple condition to write down. And this maybe explains, so the fact that the simplex category, the cyclic category appears here explains maybe a little bit why originally when Dikov and Caprano first introduced two Segal objects, they were mostly interested actually in cyclic two Segal objects, because this additional cyclic symmetry on the triangles, it allows you to construct invariants of marked surfaces by gluing by gluing this local data of these triangles along the triangulation of a surface. And for instance, they use this to define topological Fukaya categories of marked surfaces. And so for cyclic two Segal objects, they are really the ones which are weakly excisive in this sense. Okay, so I'm basically out of time. So let me just quickly, the last thing is just an outlook about similar things one can do in some simplified settings. So if the target category is an additive infinity category, which just means it has products, co-products, and the homotopy category is additive. So this is a very simple condition. So for instance, spectra or some subcategories thereof, like there are many examples of additive infinity categories. Then actually this whole picture simplifies drastically, because then in my thesis, I also prove an infinity categorical version of the Dold-Kahn correspondence, which shows that simplicial objects in this additive category C, together with a technical condition, which I don't want to mention here, but which is very weak, simplicial objects can be modeled as coherent chain complexes in C. And under this condition, the lower odd Segal condition coincides with the even Segal condition. So the discrepancy between these two goes away, so they just coincide. And on the complex side, they just correspond to those complexes which are truncated. So they go from degree 0 to k, and then they stop. Then there's only zeros. So in this additive setting, these Segal conditions have a very natural interpretation, just in terms of chain complexes being truncated at a certain degree. And if the target is even presentable and stable, then one can actually relate 2k Segal objects with from gamma, so there's an additional symmetry of the symmetric group with actual excisive functors in the sense of goodwilling. But I don't have time to go into this, so I think I will stop here. Thank you all for your attention.
All right, thanks very much, Tashi, for a great talk. And we have our usual silent round of applause for a moment. And then if anyone would like to make a comment or ask a question, please go ahead.
Yeah, I have a little confusion, I think, in my head. So one of the main theorems was that an object is 2k minus 1 Segal if and only if it is k polynomial, right?
Yeah, so this one here on the left.
Yes, exactly. So in particular, it is a Segal. It's a Segal if and only if it is one polynomial.
Exactly, exactly.
So does Segal? Is there some completeness condition here, or so?
No, there is not.
Just Segal, right?
Yeah. So if you actually want to have Resks infinity categories, you have to put completeness. Yeah.
So if I remember right, wasn't there a theorem that the polynomial of degree k lie in all pre-sheaves as a left exact localization or something like that? Is that true?
Yes, that is true. So that's just a very formal statement. So these Segal conditions, they're just abstractly, you have some diagrams in delta, which you came up with in some way. I mean, in this case, there's some limit diagrams or whatever, but you just have some diagram and you require the functor to send those to limit diagrams. And since there's only a small collection of such diagrams, just because delta itself is a small category, it just follows from formal properties that as long as your target is, for instance, presentable, so if you have enough limits and co-limits, then you always have a localization. So how to say this? So you have all functors to see, and inside there you have those functors which send some class of diagrams to limits. Yeah. And there will always be an adjoint and to this inclusion, which exhibits it as a localization. So this is just a formal thing which has nothing to do with Segal properties specifically. This is just whenever you have a functor and you impose some limit, some condition that some diagrams go to limit, you always have this localization. As long as this class of limits is not too big, but that's trivial in this case because delta is a small category.
Yeah, the part I'm confused by is, so if C is spaces, say,
yeah,
then doesn't this imply that the infinity category of Segal spaces is a left exact localization of simplicial objects in spaces?
It is Sorry,
so the
left.
left exact part is what confuses me.
Sorry, what do you mean by left? That the localization functor is left exact?
Exactly.
No, this I don't know. I just know that the localization functor exists.
Okay, I just, so maybe I remember it wrong, because that's the thing that confuses me. I thought there's a theorem that polynomial functions of degree k arise as a left exact localization.
Yeah, this might be true in Goodwillie calculus, but I'm also not sure about this. So the localization functor certainly exists, but okay, now I get the point. So your question is not about the existence of the localization functor, but about it being left exact. Yeah, this I don't know.
The Segal spaces are not. That's
right.
But I'm confused.
Yeah, so then they're not. Okay, yeah, no, this claim I certainly don't want to make, but the only claim I want to make is that the adjoint exists.
Okay.
But this is for formal reasons.
Okay. Then maybe I just remembered wrong. I should look it up.
Yeah. So it might be that in Goodwillie calculus, because there there are some stronger statements that the excisive functors in, yeah, I think in Goodwillie calculus this might be true, but I also have to look this up. I'm not sure. Yeah. Okay. So, yeah, so this polynomiality condition is slightly, it's not exactly the same as the one in Goodwillie calculus, right? So that's one has to be. So because in Goodwillie calculus, you only have, so you have the condition that strongly co-Cartesian squares are sent to Cartesian squares. Okay. And here you have bi-Cartesian.
Yeah, I see.
Any more comments? Or sorry, go ahead, yeah.
Do you know anything about can you say anything about the category of two whatever Segal objects or spaces, like about the structure they have?
No, I don't know much about this. Okay. No. So yeah. Okay. So you mean if it has like, limits, and you mean that sort of thing?
Whatever. Yeah.
Yeah, nothing except for like the formal things. Like, I mean, of course, just from being localization, it has some properties, but other than that, I don't know much. I mean, of course, for one Segal, one knows, of course, a lot, but for this higher, it's hard. Like even, for instance, computing these approximations is really hard, I think. Like computing these, for instance, what's the 3 Segal approximation of some arbitrary simplicial sets? I think, so they exist for formal reasons, but there's no, for instance, in Goodwillie calculus, there is a very nice, there's a very nice construction of this adjoint, of this approximation functor, but there is no, I don't know of any such thing in this setting, but maybe that's just my lack of knowledge.
Mm-hmm. All right, thanks.
Any more comments or questions?
So sorry, maybe just to this question, of course, in the additive setting, one can say a lot, because in the additive setting, since you can translate it to these truncatedness conditions, now you suddenly can say a lot about, like if, for instance, it will have finite limits and like everything which you can compute point-wise, it will have, because this is such, this category here, you can, it's a version of a pre-sheaf category on some shape of chain complexes. One has to make this precise exactly, but there's a shape of chain complex, and then it's just pre-sheaves. And then, of course, this truncated next condition, it's just a pointwise condition saying that there's 0 objects in a lot of places. And so everything which you can compute pointwise will preserve this condition. So like limits and co-limits and stuff like this.
I mean, limits and co-limits, I suppose. I mean, you just explained in the beginning that it's always localization is a set of maps, right? So
yeah, so that gives you one side. And then I guess if you're in the additive context, then you will get the other side for free. Exactly.
Thanks.
Anyone else? If you have a question, comment, feel free to speak. Well, if not, then let's thank Tashi again for a talk. And so next week we have Raphael, I think, stands out talking. So look forward to that. So we can stop recording.